Good morning, dear students. Welcome to this session on prestressed concrete. Uh, Till the last session, we have completed the unit 3, which is the loss of prestress. So we have talked about totally 6 types of losses that are possible for a prestressed concrete member. Uh, and we have seen some examples how to calculate the loss of distress also. Now coming to the unit 4, this you can divide into two major parts. One is knowing the flexural strength of the section, uh, maybe a rectangular section or a T section or I section, whatever it is. Knowing the flexural strength and also designing for flexure, that is one part of unit 4. The other part is to calculate deflections and to see how to control the deflections or the deflections that you calculated, whether they are within the limits or not. This is the other part of unit 4. So majorly there are two parts. So designing for flexure is one thing. I mean, estimation of strength, uh, uh, the capacity, flexural capacity you can call it. So capacity of this section in flexure and also designing for flexure is one part, and the control of deflections is other part of unit 4. Okay, so and if you want to see in detail the contents, we'll talk about types of flexural failures. So I have mentioned where it will be available in textbook, your prescribed textbook by N. Krishnaraju. So chapter 7.1 talks about this, and code procedures we'll talk about for flexural design. Uh, that is also mentioned in uh, 7.3 chapter from your prescribed textbook, and we'll design sections for flexure that is given in uh, 12.1 of your textbook, chapter 12.1. And we'll talk about control of deflections, which is available in 6.1 of your textbook, chapter 6.1. And then factors influencing the deflections is in 6.2, and prediction of short-term and long-term deflections, that means calculation, calculating short-term deflections and long-term deflections. Uh, there are two types of deflections depending on the time factor, which will the member experience immediate deflections, that those are short term. Over a period of time, we'll have deflections, that is long term deflections. So that also is being given in IS code. We have to follow the IS code for all these calculations. That also we will see. Okay, so these are the contents in chapter 4. So you can see uh, half of the syllabus is on purely flexure. I mean, uh, limit state of collapse, you can say. The other one is deflection, a limit state of serviceability. So both it is covering the unit 4. Okay, right. Let us talk about the first one, types of flexural failures. Okay, so you already have some knowledge in this types of flexural failures. So flexure in the sense when a member is in bending, we call it is under flexure. Okay, bending means it happens due to what type of loads? So lateral loads create flexure in concrete sections. So lateral loads are again as a result of dead load, live load of the beam. So they are other way called as gravity loads. So weight of a particular member and also live loads, weights of mobile things like uh, whatever it occupies in that space that you created, maybe furniture, maybe mankind or something. So this is all the livestock, live load. Okay. So due to dead load and live load, I mean gravity acting vertically downwards, the member will be in bending. I mean the other way called as technically called as flexure. Okay. So when a member is in flexure, when a member bends, how it is going to fail, uh, you know, from the design of reinforced concrete structures. So basically, you have where what you have studied in RCC. I'm comparing. So you have studied three types of members in RCC. One is under reinforced concrete beam. Second one is balanced section. Third one is over reinforced RCC beam, right? Over reinforced concrete beam. So these three you have got an idea from RCC, reinforced cement concrete. Okay. So when an RCC fails, it has to fail in any of these three conditions, depending on whether it is under reinforced section, balanced section, or over reinforced section. Now let us see what are the types of failures, uh, types of flexural failures in case of pre-stressed concrete. Okay, so first one, as you are looking at it, fracture of steel in tension. Okay, so when this happens and what happens, you have to understand completely the difference between RCC and pre-stressed concrete. So RCC, you have concrete to take compression, steel to take tension. Now pre-stressed concrete, it is completely under compression, no tensile stresses. Just for the sake of discussion, let us say we won't allow tensile stresses in concrete, pre-stressed concrete. So we have induced compression. So whatever tensile stresses come from bending of the member, those are also counteracted by the compression, and finally the entire section is in compression. Okay, so this is what there is a steel in pre-stressed concrete also, but that is only for tensioning purpose, not for taking the tensile stresses. Okay, right? So because there is no tensile stresses, right? So there will be tensioned steel, untensioned steel in pre-stressed concrete. Tensioned steel means which you pull the tendons, that is called tensioned steel. Untensioned steel, just normal HOSD bars that you provide in RCC, that is. So untensioned steel is optional. Okay, whether you provide it or not, it is your wish, right? Untensioned steel is not necessarily be provided. Okay, there is no necessity for untensioned steel. Got it? So this is what is the difference. Now there is a difference in failure types also, right? Okay, right. So coming to the first type of failure, fracture of steel in tension. When this happened, why this happened? Okay, right. Due to fracture of steel in tension zone, pre-stressed member will fail suddenly without any warning. Because what happens? This will happen when the percentage of steel provided is very low, very low. Okay, so imagine that in tension zone, you have tensile stresses. Even in pre-stressed concrete, you allowed for tensile stresses, and you have provided very nominal steel, very low steel. Okay, so in such cases, this happens. This failure type happens. Okay, so if you have a pre-stressed concrete member in tension zone, the steel provided is very low. Okay, got it. So hence the concrete in tension zone cracks. Okay, so additional tensile stresses. Once the concrete crack in tension zone bottom, the stress that is taken by the concrete will now be transferred to the steel. So this is unexpected, right? See, concrete has got some compressive stress in it. So when the load comes on it, it is balancing the tensile stresses. Once that is crossed, the compressive stress value, say for example, 10 megapascal compressive stress you have induced. So you have got 12 megapascals of tensile stress coming from the loads. What happens? It can bear up to 10. So if it is beyond 10, it cannot bear. So concrete gets cracked. This 12 megapascal has to be taken by the steel, whatever you provided at the bottom. So this is what is unexpected. Hence, this additional tensile stress now will be transferred from cracked concrete to the steel, which it cannot handle because you have not estimated. You have just provided a nominal steel which you did not, uh, no, which you thought of 10 megapascal will be taken by concrete, and there will be only 2 megapascals remaining. For this 2 megapascals, I can provide a very low value of steel. Now what is happening? Instead of 12 megapascal has come and fallen steel. That is a problem. Okay. So this is a type of failure which you encounter when there is a very low percentage of steel provided in tension zone. Okay. So this can be prevented by providing minimum percentage of steel, whether you need it or don't need it. You have to provide some minimum percentage of steel value. Then you can avoid this, or you can prevent such type of failures. Okay. So this is fracture. So what happens when once this sudden change of stress in steel will make the steel to fracture. So that is the failure. Okay, right. So what is this minimum amount of steel that is required to take care of this type of failure, steel fracture in tension zone? Okay, so that is given by the IS code in class 19.6.3.3. You can just open your IS codes, IS 1343 2012, go to class 19.6.3.3. That will provide the information regarding the minimum percentage of steel to be provided. So let us see. I'll just show you that particular class available, so that it will be easy for you to identify. So always look for IS codes for a particular required uh, classes related to your study. So let us go to class 19 point. Yeah. So 19.6.3 talks about untensioned steel, detailing of reinforcement in prestressed concrete. Reinforcement in the sense we must be careful in understanding it is untensioned steel. There is tension steel also available, but what we talk about is untensioned steel. Okay, and that too, this is going to give you 19633 about longitudinal reinforcement. So this is what we are talking about. The amount of steel that is to be provided minimum. Okay, so this is the class. Page 27 of your IS code talks about this. Okay, so this is what I mean to show you what exactly is the minimum steel required. So let us see. Minimum longitudinal reinforcement shall be 0.2% of the total concrete area shall be provided in all cases except in case of pre-tensioned units of very small sections. Okay. So for example, if you have a 100 by 200 member, okay, so 0.2% of this area, 0.2 divided by 100 into the area 100 into 100. I mean 100 into 200. So this 100 goes. So finally, this will be 0.2 times into 200. So it will be like 40 mm square is the steel minimum steel that is to be provided. Okay, right. And this reinforcement may be reduced to 0.15% in case of high yield strength deformed reinforcement. If you provide nominal steel, this is a percentage, and if you want to use HYSD bars instead of nominal steel, normal steel, HYSD bars if you are using, you can just go for 0.15% only instead of 0.2% is the minimum HYSD bars reinforcement to be provided. Okay, got it. So this is about minimum steel. The percentage of steel provided, both tensioned and untensioned taken together, should be sufficient so that when concrete in the pre-compressed tensile zone cracks, the steel in a position to take up the additional tensile stresses transferred onto it by cracking of the adjacent fibers of the concrete and a sudden failure is avoided. So you just cannot say, for example, if this is the stress diagram where, as I said, this is like some 15 megapascal, and it's about some 10 megapascal. So this 10 megapascal, you just can't imagine that it will be not taken by concrete, and we don't expect any cracking on and all that. Okay, so you have to anyhow, uh, whether it is taken by concrete or not, you have to assume that. Okay, you have to assume that is what it is shed in this third point should be sufficient so that when concrete in the pre-compressed tensile zone cracks, this is the pre-compressed tensile zone. If this is cracked, you have to assume that if it is cracked, where this 10 megapascal should go, it has to be taken by the steel provided. Uh, that is what. So both the untensioned steel, you have tendons here, and also you provide some nominal HYSD bars. So both together uh, shall be capable of taking this transferred stress from steel, from concrete, cracked concrete to the steel. That is what. So you just can't let it, the concrete, take the stresses which develop at bottom. You have to assume that once, if at all concrete cracks, that the stress shall be taken by the steel. So for that you need sufficient amount of steel to be provided, right? When the depth of the web exceeds 500 mm, the longitudinal distribution reinforcement not less than 0.05% of the area of the web shall be provided on each face. So if this depth of the beam is more than 500, in case of RCC it is 750, in case of prestressed concrete it is 500 mm. So depth of the beam, if it is more than 500 mm, you need some side face reinforcement also. Okay, this side face reinforcement, it is to be distributed on both the faces. So that is to be 0.05% of this area of the web. Okay, if it is I section or flanged sections, we call it as web. If it is rectangle, entire thing is a web. Okay, right. So the spacing of individual bars of such reinforcement shall not exceed 200 mm. So even the spacing cannot be more than 200 mm. So whatever steel you design, okay, so this shall be uh, the guiding principle. 0.05% steel shall be provided, and you shall see that the spacing shall not exceed 200 mm. Okay, and all untensioned reinforcement shall be restrained in the lateral direction. Means sufficient number of stirrups shall be designed. Okay, like this. Sufficient number of stirrups shall be designed so that to restrain, means to hold each and every longitudinal bar, okay, which is running in this direction. These are all the bars which will run in this direction. Okay, to hold all these bars you shall have sufficient number of shear reinforcement, means shear rings, loops, likewise. Okay, shear reinforcement. Okay, all untensioned longitudinal reinforcement shall be restrained in the lateral direction by sufficient number of shear reinforcement or the rings, that general language. Okay. So sufficient steel shall be provided. So this is about the minimum steel clause which is available to avoid fracture of steel in tension. Got it? So what is fracture of steel in tension, when it happens, and to avoid or prevent this, what is to be done? we have talked about. Okay, got it? So 0.2% if you use Fe250 mild steel. If you use HYSD bars, it can be 0.15% of the cross section of concrete is the minimum longitudinal reinforcement to avoid that fracture of steel, right? Uh, and the percentage is not only 0.15. The other clause is whatever stress you get at the bottom tension zone, if if concrete cracks, okay, all that stress will be transferred to steel. So the designed steel shall be, capable of taking that value. Such in such a way, you have to design that untensioned steel. 0.15 is one criteria. If the stresses are heavy, uh, based on the stresses criteria, if it is demanding some 0.25%, you shall provide 0.25%. Okay, we will not stick on to this 0.15%. Okay, and if the depth of the web is more than 500, side face reinforcement is mandatory, and spacing is restricted to 200 mm, and side face reinforcement shall be 0.05% of the area, cross sectional area. Okay, and also all that longitudinal reinforcement provided, shall be restrained accordingly, in the sense lateral direction lateral direction for this longitudinal bar is stirrups, so provide sufficient number of stirrups. Okay, that is first type of failure. Okay, we'll talk about rest of the failures next section.